And welcome back, AP Calc students. Time for another free response question from old AP exams. Today we are looking at AP Calc AB. The year is 2018 and the question is number 4. So, immediately upon seeing this question, you see there is a table of values. Therefore, you could probably correctly assume it's going to be a table of values style of question. So whenever we get a table of values, frequently what happens is, instead of given a function, we're given selected values. And we're going to have to do some graphing and approximating the area under the curve. So let's see what this question's asking about. And let's see if we can put it all together. So, it says the height of a tree at time t is given by the twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table. Okay, seems pretty straightforward, so let's take a look at the values on the table. So it looks like after 2 years, the tree is 1.5 meters high, and after 3 years it's 2, 5 it's 6, 7 years 11 meters, and 10 years it's 15 meters. So as time goes by, the tree keeps getting taller. That seems pretty straightforward. And so if h is just how tall the tree is, and their selected values, okay, seems pretty good. Now, because we've done these kinds of problems before, we're going to just right away go to this graph. And so we're going to plot this just so we have something to work with. This is actually a relatively easy graph here because it's always increasing, everything's positive. So I'm going to put this off to the side, and I don't have any negatives to worry about. And so this horizontal axis is time, and we have 10 units to figure out here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we actually need 10. And the first value they give us is actually 2. And then they give us 3. They jump to 5. And then they jump to 7. Okay? And now vertically we go from 1.5 to 15. So let's put this way at the top. We'll call that 15. And then a little bit lower, that'll be 11. And a little bit lower, that'll be 6. And quite a bit lower here, that'll be 2. And then we'll be at 1.5. Okay, and this was in years. Okay, so it looks like after 2 years, we were at 1.5 meters. After 3 years, we were at 2 meters. And at 5, we were at 6. And at 7, we were at 11. And year 10, we were at 15. So the tree just keeps getting taller. So what we don't know is what the tree was at t equals 0. That's not known. You don't know if the tree, maybe it was, maybe they counted this at when it was planted from a nursery. So maybe it was already a foot high or a meter high or something like that. Or did you plant it from a seed? You don't really know. Not really important. So we'll just connect this just to give us an idea what's going on. And again, this is the function h. How tall is a tree over the period of time? Again, a very basic concept here. So let's see what they say. For part A, it says, use the data in the table to figure out what is h prime of 6. Okay. Well, let's figure out what is h prime. If this is the height the tree is, the derivative of something is the rate that it's changing. So h prime is going to be the rate the height of the tree is changing at the 6th year. Now, because it says estimate, that's the big clue that you're going to have to use Algebra 1. And every time they say estimate, they give you a value in the middle of the interval, or they give you the interval. So if we go to 6 right here, they want us to estimate the derivative. And if the derivative is the slope of the tangent, we don't have a function, so we're going to have to approximate with the slope of the secant. So we're going to have to use 5 and 7. So we're just going to go to here and say, okay, well, I'm going to do h of 5 minus h of 7. And you can go h of 7 minus h of 5. It doesn't really matter because it'll all turn out to be the same. And I'm just working left to right. So I'm saying, okay, h of 5 minus h of 7 over 5 minus 7. Okay, so if we go to the table, h of 5 was 6, and h of 7 is 11, and then we have negative 2 here. So it looks like we have negative 5 over negative 2, or we have 5 halves. Now, to make sure we get our label correct, this was in meters, and so the rate that it's changing is going to be 5 over 2 meters per year. Okay, so find h prime of 6. So it says explain the meaning in the context of the problem. The meaning in the context of the problem is the height of the tree is changing at an estimated rate. We found A rock, an estimated rate of 5 halves meters per year at time is equal to 6. Okay? That is what that means. Okay? Let's move on. Part B. Part B says, explain why there must be at least one time in the interval between 2 and 10 such that h prime of t is equal to 2. Well, if you're ever asked to explain why something must happen, probably you're either going to be using the intermediate value theorem or the mean value theorem. Because if something's supposed to happen over an interval, those are the two things they love. Well, if you want to know which one is which, this says explain why over the interval we have h and they're asking about h prime. There's a big clue that it's the mean value theorem. So let's do a quick review of that. So the mean value theorem, always good to review these theorems. The mean value theorem says if I have a function that is closed or is differentiable and continuous on the closed interval. So here is my function. Here's my interval. I'm just going to say from a to b. Okay. What the mean value theorem says is that if you take the slope of the secant or the average rate of change, okay. So if the slope of the secant, which is equal to a rock, which is equal to algebra 1 slope, f of b minus f of a all over b minus a. All of that means the same thing. The mean value theorem says that if a function is differentiable and continuous over the interval, then the following is true. There is some place in this interval where the slope of the tangent, which is the derivative, which is the instantaneous rate of change, there's somewhere in this interval that the slope of the tangent, so I'm just approximating there would be the slope of my tangent right there, is equal to the slope of the secant. So I would say here f prime of c. There's some c value in the interval, they usually say. So it'll be a c value. So I'm going to say it's about right there. Okay, and we know that the c value is equal to I rock, which is equal to the slope of the tangent. All right, all of these things. This is the guts of the mean value theorem. Okay, if I give you a rate of change, an average rate of change, then somewhere in the interval is an instantaneous rate of change that's equivalent if the function's continuous and differentiable. That's what it means. So the clue on this question is, it says, explain why there must be a time in 2 to 10 such that the derivative is equal to 2. Well, I'm very suspicious. If they want me to prove this, I'm going to bet that we're going to find that the A rock is equal to 2, but we have to find out. So let's see. So let's see if we can figure out what the average rate of change is over the interval. Now, if you have already tried this problem and you're struggling and trying to figure out what in the heck's going on, this is one of those extremely rare situations where the AP actually has a typo. Super frustrating. Well, here's what wound up happening. What they accidentally did here in their reprint is they copied the domain of question C into question B. So the domain here from 2 to 10, what this should have said was explain why there must be at least one time t, not in the interval from 2 to 10. It was supposed to be in the interval from 3 to 5. So you immediately want to do this. I'm going to cross this out. And I'm just going to write my new domain here, which is going to be 3 and I believe we were less than or equal to t, less than or equal to 5. So that's what we're going to be looking at, 3 to 5. If you tried to do it the other way and were confused, that's why you were struggling. You get a different conclusion. So let's go ahead again and let's see if we can figure out what our average rate of change is over this interval. So it looks like what we're going to be doing is doing h of 5, and we're going to do minus h of 3 all over 5 minus 3. Well, h of 5, according to the table, we're getting 6. And so that was at 5 minus 3. And that h of 3, according to the table, that's going to be 2. So it looks like we get 4 over 2, which is equal to 2. Well, that's handy, because look at the question. It says explain why there must be at least one time t in the new interval here, where the derivative is equal to 2. Well, our average rate of change was 2. Our instantaneous rate of change is 2, so we've got it. Okay, so now that we've proven this, we can say the following. Okay, so our conclusion is, because function h is differentiable and continuous. We always have to state that. Because h is differentiable and continuous over 3 less than or equal to t less than or equal to 5, okay, by mean value theorem, there exists a c value in 3 less than c less than 5. So we're just saying the c value is in this interval such that the derivative of h evaluated at c is going to equal 2. And it's okay to end it right there because part of our justification is showing this work up here. So I'm demonstrating my a rock being 2, and this is my I rock here, and I'm saying, since I've just shown you that the a rock is 2, because this function here is differentiable and continuous, by the mean value theorem, there is a value in the c in the interval such that the derivative, or instantaneous rate of change, is equal to this right here. Okay, so that was the key. Okay, a little mean value theorem practice. All right, let's jump to C. C says, use a trapezoidal sum with 4 subintervals indicated by the data in the table to approximate the average height of the tree over the time interval 2 to 10. Okay, well, before we do our trapezoidal sum, we knew some kind of approximation was going to have to come up. It says, use this to approximate the average height. Now you got to be careful. It was really easy to miss a point on here. Many students missed the average height part. So remember, quick review here, which is also good to look at. Remember, whenever you're asked to find average value, okay, so average value of a function is always equal to 1 over the interval the function's being talked about times the integral of the function over the interval. Okay, that's average value. So what they're wanting is average height, so our function is just h. So we're going to apply this to the interval they're talking about, which is, in the question, it is from 2 to 10. Okay, so our a value is 2, our b value is 10. And so this is going to wind up being 1/8. So what we're figuring out here, since we have this, we're going to find the average height. So the average height is equal to 1 over, I hope we can agree that that's 8, because it's going to be, the interval here is from 2 to 10, and then we're going to multiply that by the integral of 2 to 10 of h of t dt. Okay, and so this is where we're going to use our trapezoidal rule. So I'm going to put an equals here, and I'm going to do 1/8. And let's see if we can use the trapezoidal rule on our graph and figure this out. Now, obviously, you don't have to use a graph, but it sure makes it easier to look at it. So they said to use 4 subintervals. So let's see what we have here. We have a value here at 2, and they said to go from 2 to 10. And so we've got 3, and we've got 5, and we've got 7. Yep, there's 4 trapezoids. And we just have to remember the formula for a trapezoid. I'm going to get rid of this mean value theorem, and we'll do all of our work under here. So let's look at our trapezoids. So our area is approximately, let's do trapezoid number 1. It's going to be the average of these two heights. Remember, when our trapezoidal rule is based on, from geometry, we would have this kind where we have base 1 and base 2, or the other way around, and if it was a right trapezoid, that would be the height. But our trapezoids are vertical, so our bases are actually vertical distances, and our height here is sideways. So these are base values. So that's base 2, and this would be base 1. So I'm averaging these two times the width, which is actually the height of the trapezoid. All right, so let's look at this first one here. This first one's going to be the height at 2. We just go to our table. So again, this is years. So at 2, it's 1.5 plus 3, or at year 3, it's 2. So those are those values. So it's the average of those times 1. There's trapezoid number 1. Okay, trapezoid number 2, I'm going to add to that one the height at 3. So the height at 3 again is 2. The height at 5 is 6. And the width of that interval is, or it's that average, okay, times the width, which is 2. The next trapezoid, the height at 5 is 6. The height at 7 is 11. It's that average times this width, which is also 2. So notice the first trapezoid, the width was 1. These next two, it's 2. And this last one, it's actually bigger, it's 3. So plus our next one, the height at 7 is 11. The height at 10 is 15. Average of that. And then the width of that interval is 3. So there are the 4 trapezoids going from left to right. Okay? And now we just have to figure this out. So let's see here. 2 plus 1.5 is 3.5. So 3.5 is 7 halves. So this is annoying. We get 7 halves over 2, which is equal to 7 fourths. That's annoying. Plus, let's see this one here. I guess our 2's cancel, and this just turns into 8. Plus this one here. Cross cancel our 2's, and I think we just get 17. This one, what do we get here? 26 over 2. 26 over 2 is 13. 13 times 3, I believe we're getting 39. Okay, so let's see. This turns into, so 7 fourths, that's 1.75. Okay, so we got to add 1.75 to all of these. So this is equal to 25, and this is going to be 40. I'm adding that one to this one, and we get 40.75 plus 25. So I'm getting 65.75 for just this part of the integral here. Okay, so 65.75 is without question the most common wrong answer, because people forget, like I was saying before, it's 1/8 of that. So I'm going to take this number now and I'm going to put that right here. Our estimate of our integral was 65.75. But now we have to multiply it by 1/8. For a non-calculator question, I think I'd have probably been fine for this, but if you felt like getting a common denominator here, what do we get here? 65 3/4, that's the same thing. And so if you convert that, you wind up getting 263, I believe, over 4. And so if we went back down here, we'd say, well, that's 1/8 times 263 over 4. So your final answer is 263 over 32. And this is an average, so the average would then just be meters, because it's the average height. So again, I think I would have been fine. I think you'd have been fine just putting this number right here, and but this is what it would be as a fraction. So I'm going to say either one of these, as long as you have your label. So whenever you get a table of values, there's always this component to it, so that's where it was. So this was actually a part of C continued up here. Okay, so C was kind of a long part of the question here. And now we have this last part, D. Okay. All right, D, let's see what it says. D says the height of the tree in meters can also be modeled by the function g. Okay, alternate method, where g of x is equal to 100x. I'm going to write that down here, 100x over 1 plus x. Now, I want to pause right here. I want to show you something that was very unusual about this function. What caught my attention right when I saw the function was the fact that they were using x and not t. Because if you notice that this height of the tree is in relationship to time. So after 2 years, after 3 years. So the independent variable is time. And as time increases, height is increasing. But they're not using t, they're using x. And so that caught my attention. I'm like, well, what the heck does x represent? And so as you keep reading, it says the height of the tree in meters can be modeled by g of x is 100x over 1 plus x, where x is equal to the diameter of the base of the tree. Has nothing to do with time. Okay, so I'm just going to write that here. X is equal to the diameter of the base. Okay, diameter of the base of the tree. Okay. When the tree is 50 meters tall, this is interesting. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. According to this model, what is the rate of change of height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? Now, I'm going to give you a little heads up. This part of the question had a very low percentage of students getting this right, because there is a very common thing to miss on this one. And so I'm just going to point it out. And this is another one of those things where you're like, oh, well, there's a lot of points available. Maybe this is where they would have burned me, because it is subtle. So here's what we got. We have the relationship of the height to the diameter of the base. No time involved here. But it does say when the tree is 50 meters tall. When the height of the tree is 50, okay, they are telling you, so when the height of the tree, because that's what g of x is, when g of x is equal to 50, the problem is saying the rate that the base of the tree is increasing is at a rate of 0.03 meters per year. So I'm going to write that down here, the rate the base is increasing. So the rate the base is increasing, well, the rate the base is increasing would be, if you wanted to use the b, you could say, well, the rate the base is increasing is equal to 0.03. You could say it that way. So that's kind of interesting. But what's also interesting is that now time is involved. So in this thing, x is a diameter, but they actually give me information in respect to time. And this was the little wrinkle that a lot of students missed. So this was a little tricky. So what it says is, according to this model, what is the rate of change of the height? So again, now they want to say, this is the height here. They want you to find g prime with respect to time, even though they gave us g with respect to the diameter of the base. So that's what's a little bit weird about this problem. So what is the change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? So at what time is the tree 50 meters tall? We don't know. We don't even have a t. So this is really kind of odd. So let's go ahead and look at what we have here. What it wants to know, I'm going to write this just so we have room here. I'm going to write the function again. So g of x is equal to 100x over 1 plus x. So this is the height of the tree with respect to the diameter of the base. And the question says, what is the rate of change of the height with respect to time? Well, what that wants you to do is this. Find d dt. Okay? So we need to find d dt of this thing when the tree is 50 meters high. So let's jump in and see what we can do. So let's take d dt of this thing. So this over here, if I take the derivative of this, I have a little quotient rule over here. So as I take the quotient rule here, I would say the derivative of the top is 100 times the bottom. Now, this is the part, actually, I'm gonna write this a little bit different so I don't lose anybody. So I'm going to take ddt of this. I just decided to put in one extra step. So what this winds up doing is I'm going to take ddt of g of x, and that's going to equal taking ddt of this thing over here, 100x over 1 plus x. Okay, so I'm taking ddt of both things. So what I want to show you, though, is on this side, this little wrinkle here. So if I take the derivative with respect to time of g, what this turns into right here is I'm going to take the derivative of the function, but my variables don't match, so I have to multiply this by dx dt. And that was the extra little step that was very, very hard to get on this one. So when you did the product rule over here, when you took ddt of this thing, there was two ways to do this. You could have just incorporated the derivative in here, or when you were done, just multiplied it by ddt. There was two ways to do it. So what I'm going to do is I'm going to do it the one way, and then I'll contrast it with the other way. So the way that would probably be most intuitive to you would to do the following. If I'm taking ddt of this, I would bet most of you would do this way. You would say, okay, the derivative of the top, which is 100. Did my variables match? No, so I have to represent with dx dt times the derivative of the top, or derivative of the top, 100, variables didn't match, dx dt, times the bottom, 1 plus x, minus the top, 100x, times the derivative of the bottom. Now the derivative of the bottom is just 1, but again my variables didn't match, so I'm going to represent with dx dt. Okay, so this whole top here, guys, I'm just going to scoot this over so we can read that a little bit better. Made it a little too tight here, so I'm just going to recopy that. So again here, when I was taking the derivative of this, I would say, well, that's going to be g prime of x times dx dt. Okay, and that is equal to, now we'll have a little more room here. So again, I said the derivative of the top, which was 100, variables didn't match, dx dt, times the bottom, 1 plus x, minus the top, 100x, times the derivative of the bottom, which is just 1, but my variables didn't match, so I got dx dt. That looks a little better. So there's the derivative of the top all over the bottom squared, which was 1 plus x, the quantity squared. Okay, that's how most of you guys would have done that. And then now that you have this, it's just a matter of filling in the values. Now, up here, I want to clean something up here, because sometimes as you're going through the problem, you write stuff down and you go, oh, I guess I could use that variable. So when I come back to here, and I want to say, when it says right here, when the tree is 50 meters tall and the diameter of the base of the tree is increasing at 0.03 meters per year, when I used a b and I said, well, the base is changing at this time. Well, the base was represented with this variable x, and so sometimes you don't realize that as you're doing the problem. You go, wait, it's not really b, because x is actually the diameter of the base. So they weren't introducing a new variable after all. It was just x. Well, that's really handy because we're going to need that in here. So now what the question says is, find, and this is another added wrinkle to this. It says, what rate is this happening at the time when the tree is 50 meters tall? Well, you guys, I have to figure out what x is. And this is where a lot of students were stuck. So what I want to bring you back to is this little formula. So remember, this is the height of the tree with respect to the diameter of the base. Well, what you had to do was solve for x. So what I'm going to do is I'm going to say, well, if g of x is equal to 100x over 1 plus x, they're telling us that the height of the tree is 50. So what you have to do is solve for x. Okay? So if you want to solve for x here, you could multiply both sides by the denominator here, and you would get 100x is equal to 50 plus 50x. Subtract the 50x over, and you get 50x is equal to 50, and you would get x is equal to 1. This little added piece right here, this is what a lot of students missed. So now actually what you're evaluating here is you're saying, oh, I'm trying to find g prime of 1 times dx dt is equal to that whole thing. So now I'm going to substitute in my values, and I'll show you what we get. All right, so we get 100 times dx dt is 0.03 times 1 plus x. Well, x is 1, so this is a 2. Okay, so 100 times 0.03 times 2 minus 100 times x. Well, x is 1, so that's just going to be minus 100 times dx dt is 0.03. Then on the bottom, well, x is 1 again, so the bottom is 4. So let me clean that up over here. So g prime of 1 dx dt is equal to, what did we get here? 2 times 100, so I'm going to call that 200 times 0.03 minus 100 times 0.03. Well, now if I just move the decimal over, that becomes a 3, all over 4. And just for the sake of space, I hope we're okay here. If we do 200 times 0.03, I'm going to move the decimal over and double it, so this is turning into 6. I hope we're okay there. So that number up top here just becomes 6. Okay, so 6 minus 3 over 4. My final answer is 3/4. Okay, so the final answer here is the tree is, according to the model, the rate of change of the height of the tree with respect to time when the tree is 50 meters tall, it's going to be 3/4 meters per year. Okay? Now, it's always a concern that when you look at one of these questions as a whole, you have one part that just, you think this is impossible, I can't do this. D was disproportionately tricky, and this would be one where, again, in the course of a test, you have points you can miss. If this followed and made sense to you, and you were like, hey, that wasn't that bad, I could do that, then that's great. If this was like, you lost me here, why is there an X and then a T, and then this was confusing. This, everybody, is definitely rare company if you're one of the people that followed that completely and got it just fine. But the worst thing that can happen is you see this kind of part of a question and you lose confidence in the other things you know. So just keep in mind that in the context of 6 free response questions, 4 parts for each one, there's 24, if you think of it, there's 24 questions on here, and all you need to get is a 65%. Well, 2/3 of 24 would be 16. Can you get 16 out of the 24 right? Well, there's going to be a few that are just going to, hardly anybody's going to get, and D was kind of like that. So if you followed it, great. If not, let's focus on the other 3, where the first one was estimate. We had to find a rock, so we had to recognize that. A rock, that was very doable. The second one was a mean value theorem question. Hopefully you got that. And part C, find average value by estimating using trapezoids. So if you felt good about A, B, and C, great. And this was just bonus material here on D. Okay. So that was 2018. Question number 4. The one I remember, the one last thing I wanted to say also on this one, if you wanted to treat this a little bit differently, you could have just taken the derivative of this and then multiplied the whole result by 0.03, because that's what this would have been. Take the derivative, not implicitly, and then when you're all done, multiply it by dx dt. That's another way to do that. It's a little cleaner, you get the same answer. But that's, in my opinion, a little more confusing. So anyway, more stuff about D that's not important as the other material. Okay, so there it is, number 4, 2018 table of values. Thanks for watching. We'll see you next time.